Hi, we continue with the PN sequence generation. So we have seen that earlier in a CDMA receiver, so that is it requires a local PN generator, and the PN generator at the receiver, it is to be with phase with uh, whatever the PN generator at the transmitter. So that's why we need to synchronize the clock for the transmitter and the receiver. But in the case of uh, received side, the PN generator is having a highest clock rate than the transmit side. We can have a PN sequence phase. Okay, so we can consider that phase of the PN sequence, and that will be changes uh, slowly. Uh, and at the time at the receiver side, we are having the acquisition phase. So in that case, we need to find out uh, what will be the clock rate and the phase for this. If we are having the phase of both the sequence match to the given filter, it produces a high output, and at which instant the clock frequency is uh, locked to the frequency of a received PN data, received PN modulated data. So now we are having a PN sequence is modulated and applied to the correlator. Then we are getting when we are having the PN sequence, when we are applying to the correlator, then we are able to receive the signal there. So we are having a local PN generator here. You can have a that receiver signal. We are having the correlated data, and this one is about your local filter, so that we can able to detect the signal. That received IF signal, which is modulated with PN, and data signal is correlated with locally PN modulated signal. The correlation sequence takes place in the IF domain. The receiver PN sequence relation to the sequence that we are having for the particular IF domain. So we can have the PN sequence which is PSK modulated, and the modulated signal is applied to the correlator. Okay, so that we have seen earlier, and then when the locally modulated signal is synchronized, phase synchronized to the received signal, the output signal bandwidth is reduced to the data modulation bandwidth, and signal pass through this narrowband filter. Okay, that happens when the correlation peak occurs, and the output of the filter is modulated data without the PN code, which is detected by the detector and following the filter there. So in that case, we are having a clock generator frequency is fixed at the recovery clock frequency. So we can have, then we can continue with this particular autocorrelation of the PN sequence with the continuation. So now this one we are having a analog correlator of a PN sequence, where the time shift of the sequence is continuous, and here if you see that the peak occurs at a 0 time shift within a 1 bit period on either side from the normal position. The autocorrelation has a triangular shape, and it is having the chip period of a TC, and that autocorrelation has a triangular shape, that is from minus TC to plus TC. The normalized peak at R of tau, we can say that it is R of 0 is equal to 1, or we can have R of t is equal to 1 by L. L is the length for the given sequence, and the autocorrelation peaks are separated by the period of a PN sequence L of TC. Okay, that is about we are having a autocorrelation separated here. Now then we can see that we can have a, a PN sequence. For the given PN sequence, we know that it has having exactly equivalent that whatever the data symbol period we are having, and that codes with period shorter than or equal to the data symbols are termed as the short codes, and the codes that repeats for each symbol, and L chips of the PN code are contained into each data bit duration TD, and that each chip duration, that is TC, we have LTC is equal to that TD. And the spreading waveform is a periodic with a short course. We can have, if we see that here we are having the short PN code, and that is about a spreading waveform. And the spectrum of the short course modulated signal is periodic with lines occurring at a 1 by LTC here. We can have this interval here, and long codes that are a PN code, it is having the length which is several data bit long, and the spreading waveform, if you see that it is not periodic with respect to the data symbol, and spectrum, if you see that it looks like a random one, and this aperiodicity, because it is not periodic here, aperiodicity of this waveform is more complex, that whatever we can say that is about the DSS signal there, that is more complex for what? For detecting the periodic short code modulated data. That's about we are having a short code and a long codes, because we are having, if that period is shorter, then we can say that it is a short code, and period is long, we can have a long code there. We can find out how much will be the gain for this particular here processing gain and a capacity of a CDM. So for that purpose, we need to know about what will be the data rate to find out the gain, processing gain in a CDMA. So here if you see the figure A, that is a data spectrum, B, that is a spread spectrum due to a CPN sequence, then C is interference spectrum, and that D is a correlated output with the data spectrum disparate and interference spectrum disparate. We can have a disparate data spectrum. So to find out what will be the gain and the capacity of a CDMA, we need to know about the data rate. Okay, that data rate when modulated with a PSK has the null to null bandwidth, and if this data is superimposed on a PN sequence at a rate, that is, we can say that supposed to be we are having PN sequence rate is a RP here, the resulting signal is spread over the bandwidth, and that signal which is null to null bandwidth for a PSK modulated PN sequence. If you consider that a carrier to noise ratio for the given particular signal, so that is about, we need to know about how much will be the interference signal that is superimposed on this particular receiver signal there. So if you consider that figure, we are having A, we can say that the BD is nothing but the bandwidth, and that what we can have a sequence data rate, that is RP, and it is to be spread for the given spectrum, that is about a bandwidth of a BP here. And when we are having a interference signal, that is about I, interference spectrum, that is I in figure C, and that interference signal can be deliberate, a jamming signal or any other undesired signal and in the receiver band. If we can have the input is a correlated signal with the PN signal in the receiver, the desired signal energy is displayed in the signal band, that is the BD here, whereas the interference signal being uncorrelated with the PN signal spread over the band of a BP there. So we can obtain that how much is gain, processing gain. It is depending upon that what will be the PN sequence data rate RP, and whatever the data rate we are having, PN rate and a data rate, and that is called as a RP by RD, and that is nothing but what? A bandwidth spreading ratio, or we can say that a processing gain, and it reduces whatever the energy per bit to the interference density ratio. This, okay, if we are having that interference ratio C by I, so then your data rate processing gain will be changes. So using this, we can find out whatever we are having a data rate there, so we can have a processing gain, that is the GP is equal to PN rate by data rate, that is RP by RD, and we can find out a E by I, that is nothing but what we are having a interference density ratio, that is about we can have a interference density. We can say that E is nothing but the energy per bit, and we can have interference density ratio, that is about the I0. We can calculate that interference density ratio in terms of what we are having a carrier to interference. We can have that is about a carrier to interference ratio and a whatever the gain, that processing gain in a CDMA here. So this one we can obtain here. Then we can find out a channel capacity based on this particular E by I ratio in terms of what we are having in processing gain, and we can add the factor for whatever the capacity we are having, a maximum permissible users in the CDMA network. Okay, so that's why the number of maximum users, okay, your max is equal to in terms of the processing gain and interference ratio. So this one is about your channel capacity. So you can obtain that how many number of users we are having, and then we can find out the channel capacity. So this one is for the channel capacity in a CDMA. Now next we can go ahead with a, so we are having FH CDMA there. Now that is about FH CDMA is nothing but what? A frequency hopping CDMA. So in this frequency hopping CDMA, the carrier is made to hop from one frequency to the another frequency. We can have, that's why we can say that it is a frequency hopping, and that frequency hopping is to be done within a particular band, or we can say that allocated band, allocated frequency band along with the modulation there. Now consider we are having a FSK system modulating here, that is about FH CDMA with FSK carrier. Consider that a binary FSK system modulated with a data of 1 by T, where T is the symbol period. The minimum frequency separation between the FSK tone is 1 by T Hz, as shown in this particular figure, and available RF bandwidth is divided between the L. So you can have that L carriers that we are having, that F1, F2, F3 to FL, and each carrier having a bandwidth of a 2 by T, or we can say that is about, that is bandwidth is nothing but the 2 by, we can have a 2 by T is nothing but the only with a bandwidth of 2 by T Hz, or we can say that is about the modulation bandwidth. And this carrier frequency is controlled by a PN generator of length L is equal to 2 raised to n minus 1 chips, and that n is nothing but the length of the shift register generating the PN sequence. So this one is about we are having a PSK hopping, and then we are having this FH CDMA system, and if you see that a frequency hopping carrier is generated with a fast frequency synthesizer. So we can have a fast frequency synthesizer to generate the frequency hopping carrier, and PN generator provides the control data for the frequency synthesizer, that is fast frequency synthesizer, and the carrier is FSK modulated by the data, and the receiver PN generator is synchronized to transmit the PN generator so that it generates the same control data for the receive side frequency synthesizer, providing the carrier frequency. This PSK demodulator detects the data using the carrier provided by the synthesizer. So then we can consider that a concept of a frequency hopping signal. We can have a total bandwidth which is to be shared, and then we are having, okay, so we can have in F1, that is about FL, that is about the total number of signals we are having. Okay, so then we can have a total bandwidth, and this is about a time So in that case, we can receive the data.